Welcome back to this last lecture of mine in this series. I took two classes introducing signals and systems, and I've had three classes so far on um, time and frequency domain analysis of LTI systems. I started off with the convolution. I did a Fourier series because the idea was for LTI systems complex exponentials are eigenfunctions. So we, based on that, we applied our ideas to periodic signals, right? And we said periodic signals can be written as a Fourier series consisting of fundamental, frequency, and of harmonics. And the entire Fourier analysis tells you how to compute those Fourier coefficients and stuff like that, right? Now, towards the end of the last lecture, we stopped at what if the signal is not periodic, right? It is aperiodic, what's called the aperiodic signal. So in this case, I had a signal x of t, as the slide shows, is defined between time t1 and t2 and is 0 outside this interval, right? So the idea is, how can we then extend the idea of this frequency domain analysis to non-periodic signals? Okay, so the approach I said was, let's define a signal x t naught, right, x t naught, uh, by repeating x of t, right, every t naught seconds. T naught is greater than t1 plus t2. T1 plus t2 is the duration of the signal. So you take any period outside this interval and repeat x of t, and that is what is shown in the figure here. If you see, I'm talking about x t naught, which is non-zero, in the time t1 to t2, but now repeated every t naught seconds, right? And this thing, the picture shows repeated, and because x t naught is periodic, Fourier series applies to this. So x t naught consists of x of t as one period and the same signal repeated. That's some kind of a mathematical construction, right? And I claim that because x t naught is periodic, I can write it as a Fourier coefficient xn and e raised to j n omega naught t from my understanding of Fourier series, where omega naught is 2 pi by t naught. T naught is a period. Okay, and I know already that xn is given by the standard Fourier series coefficient integral 1 by t naught integrated over any one period t naught, x of t, that's a signal in one period, right, and e raised to e raised to minus j n omega naught t dt. That's the standard definition of xn, right? I now introduce two more ideas. I first say, since x of n is 1 by t naught integrated over t naught, x of t e raised to minus j n omega naught t dt. So let me define x of omega. So this is my new definition as minus to plus infinity x of t e raised to minus j n omega naught t. So I make use of the idea here that x of t is limited between minus t naught by 2 to plus t naught by 2, right, and it is 0 elsewhere. So the limits can be taken to be from minus t naught by 2 to plus t naught by 2 instead of minus infinity to plus infinity without altering the definition. So when I do that, you can see that this becomes similar to xn. So in fact, I introduce another definition that says, except for this t naught, so this part is x of omega, so it is x of omega by t naught. So xn, well, and omega now taking specific values of n omega naught. So xn, the moment I define x of omega, xn can be defined as x of n omega naught by t naught. Okay, that's the, these ideas come from construction, right? I take x of t, repeat it every t seconds, every t naught seconds, make it periodic, call that as x t naught, and the moment I get x t naught which is periodic, the entire Fourier series ideas apply to that. So I can continue to write xn in terms of xt, and I now define two new things. One is x of omega, other is xn in terms of x of omega. Okay, so this is where I had left last time. Then now I play around. What if I change my t naught, right? The periodicity with which I repeat x of t, right? I'm taking x of t, repeating it every t naught seconds. So what if I increase the value of t naught? That's the question I'm going to ask now. Right? So for some t naught, I've sketched xn in the slide here, where I've taken x of omega, I've taken some arbitrary shape. This is x of omega, and this is omega axis, right? And I say, okay, let me make it as x of omega by t naught. So scale this by t naught for some t naught, and n omega naught will be one value here for n equal to 0, one value here n equal to 1, that's the fundamental frequency, one value here second harmonics. So this is omega naught, this is 2 omega naught, this is 3 omega naught, and so on. Similarly on the other side, minus omega naught, minus 2 omega naught. So this is what I get for some value of t naught. Okay, what I now do is I increase t naught by a factor of 2, right? I increase t naught by a factor of 2. You see here that t naught occurs in the denominator. When I increase t naught by a factor of 2, the height of this comes down by a factor of 2, because denominator is doubled, numerator is same. So I now have a smaller height. So this is for the new t naught. This t naught is 2 times this t naught. So this height is half of this height. Okay, and what happens is omega naught is 2 pi by t naught. If t naught increases by a factor of 2, omega naught decreases by a factor of 2. It comes closer. So here was omega naught for the old value of t naught. Now omega naught moves here. This is omega naught. This is 2 omega naught. This is 3 omega naught, and so on. So what was occurring with sufficient space, now these three values for omega naught, 2 omega naught and 3 omega naught move closer, right? Similarly on the other side, minus omega naught, minus 2 omega naught, minus 3 omega naught, and so on. Okay, so what I'm going to suggest is, if I now go on doubling t naught, this is one value of t naught, this is after it is doubled. If I double it again, then this height comes down and these points move even closer. You double it again, these spectral lines move closer together, right? So I'm saying you go on doing this, and in the eventually what happens, that's a question, right? Eventually what happens is these discrete lines completely cover the x-axis, and the height becomes infinitesimally small. Okay, and that's what I'm going to say now. So I'm going to suggest that in the definition, then if you substitute for xt naught in the previous case, xt naught was summation xn e raised to j n omega naught t, right? First definition is xn, by this definition, is x of n omega naught by t naught into e raised to j n omega naught t. Okay. Now you apply the limits, go on doubling t naught. If you go on doubling t naught, right, t naught will approach infinity. Okay, and omega naught, which is 2 pi by t naught, will approach 0, because t naught occurs in the denominator, right? So this becomes an elementary function to omega, delta omega. So delta omega is when omega naught approaches 0 when T naught becomes infinity, right. So in this case you can replace 1 by T naught by omega naught by 2 pi. So in my here what I am trying to do is, in this equation you keep x n omega naught as it is. So this value 1 by T naught can be written as delta omega by 2 pi, right, equal to 1 by T naught as T naught approaches infinity, right. You bring 2 pi on the other side, omega naught has become 0, approaching 0, so it becomes delta omega. So delta omega by 2 pi is 1 by T naught. So that's what I write in the next slide here. I say that it is delta omega by 2 pi, right. So 1 by T naught is replaced by delta omega by 2 pi, and in this case, right, n omega naught is now, omega naught becomes extremely small, right. So n omega naught becomes a continuous variable, okay, and so this is a continuous variable, this is a continuous variable. So I'm saying as T naught approaches infinity, okay, this summation over n becomes an integral, okay, and from minus to plus infinity, this is x of omega, this is e raised to j omega t, and there is a 1 by 2 pi now that you can bring it out into d omega, that is this delta omega that is there, that becomes the variable of integral d omega, and that's what is written here. So I have x of, and in the limit as t naught goes to infinity, this becomes equal to x of t, right. So on the left hand side I have x of t. So you see here in this first boxed equation I have x of t on the left hand side, 1 by 2 pi, that comes because omega naught and t naught are connected by a 2 pi statement. So 1 by 2 pi minus to plus infinity x of omega e raised to j omega t and d omega. That's the inverse Fourier transform equation, right. And as we said before, x of omega is given by this integral. So I have two integrals shown there in boxed items in the slide. This is the inverse Fourier transform and this is the Fourier transform. The two boxes in the slide refer to these two statements. This is the Fourier transform and this is inverse Fourier transform. Turns out that it is a unique operation for every x of t. When this improper integral exists, right, for every x of t I can compute x of omega. For every x of omega, when this improper integral exists, I can get back the x of t. So it's a two directional operation. From x of t I can get x of omega, from x of omega I can get back x of t. Okay, so it's a one to one mapping. If two x of t's give me same x of omega, then they should be identical for all the times. Okay, so that's a Fourier series in a nutshell. Okay, and if you look at these integrals, even when x of t is real, right, because I'm multiplying this with e raised to minus j, right. Okay, I think there's something wrong here. It should be omega. Okay, because I'm multiplying this with e raised to minus j, that's complex, right? Because e raised to minus j can be written as cosine minus j sine. So I have complex. So even when x of t is real, this integral can give rise to a complex function here. So x of omega can be complex, right? And because it is complex, it has either the real or the imaginary part or the magnitude and phase. That's what I've tried to say here. So even for real x of t, I can get x omega complex, which has its magnitude and phase. Okay. So I think in the next slide I'm taking an example. I'll take the example and then we'll take some questions. So let's take a simple example, x of t, that is non-periodic Okay, in this case, e raised to minus a of t u of t. Okay, this is some non-periodic x of t that I have taken. This is x of t, this is t, this value is 1, and it is 0 for t less than 0. This is the given x of t. Obviously, it is non-periodic. I can apply Fourier transform and compute x of omega. It's given by minus to plus infinity x of t e raised to minus j omega t d omega, sorry, dt. Okay. So substitute x of t is defined from 0 to infinity. So these limits now undergo small change. Minus infinity to 0, it is 0. So I just need to integrate from 0 to infinity. X of t is e raised to minus at in this interval, e raised to minus j omega t dt, right. Carry out standard integration, right. Let's assume this integral exists, right. We will have to worry about that because it's an improper integral. Every time I have an improper integral, I worry about its existence. For what value of a it is defined, right. So this is minus to plus infinity e raised to minus a plus j omega into t dt. Okay. If you see here, this absolute value of this is e raised to minus at. Absolute value of the second factor is equal to 1, right. So that doesn't change with the time. So I need to worry about whether the first function decreases or not. That will decrease if a is greater than 0. So as long as a is greater than 0, this integral will exist, right. Assuming a is real, a has to be greater than 0 to make this factor e raised to minus at decrease. Otherwise, this integral is not defined. Okay. So let me emphasize again, any improper integral, before you carry out integral, you take a step back and see for what values is the integral defined. In this case, turns out that only when a is positive, this integral is defined, because this factor will then decrease. Once you make sure that a is positive, then it is very simple. It is going to be a plus j omega, right, with a negative sign, e raised to minus a plus j omega t. Substitute 0 to infinity, right. You see that at infinity this goes to 0, at t equal to 0 this goes to 1, and because it's a lower limit, that and minus cancel each other. So I get a plus j omega. So for this particular x of t, its Fourier transform, now I'm going to use this symbol two-sided arrow to indicate x of omega, its Fourier transform, it is 1 by a plus j omega, and it is complex. X of t is real, but its Fourier transform is complex. Okay, so because it is complex, I need to worry about its magnitude and phase. Okay, otherwise, I can't plot it. So its magnitude is magnitude of this. Magnitude of numerator is 1. Denominator is a square plus omega square under root. So it is 1 by a square plus omega square under root, right. And its phase is, this contributes of phase is 0 because it is real. This is the denominator, so it becomes minus, right, and it is tan inverse omega by a. Okay, so I now sketch the magnitude and phase of the Fourier transform by varying omega in both the directions, from 0 to infinity, 0 to minus infinity, right. So I'm sketching here the magnitude is under root 1 by a square plus omega, and phase is minus tan inverse omega by a. So let me sketch them here. First, taking some value of a, you can see that when omega is very small, when omega is close to 0, then magnitude is 1 by a, right. So this value this value, the peak occurs at omega equal to 0, that's 1 by A, and as omega increases, that dominates more and more, so it is 1 by omega, right, and so you can see it is falling off as 1 by omega, right, on both the sides. And if you look at the angle, when omega is close to 0, tan inverse 0 is 0. So for angles around omega equal to 0, you will see very small values, but when omega becomes very large, right, tan inverse of infinity is pi by 2 with a minus sign, minus pi by 2. When omega is negative, it is minus pi by 2 and minus, so it becomes plus pi by 2. So you see here that omega small, the angle is 0, and omega very large, the the angle tends to become minus pi by 2. When omega is very large on the negative side, the angle tends to become plus pi by 2. Before I go further on this line, let me stop and take questions. I'm now going to do several more functions and compute the Fourier transform and look at its properties, and then come back to LTI systems. So what I want to do today is today is the last class, so I will try to do live interaction, right, instead of doing it online. I want colleges to raise their hands and discuss. I can then come back and continue from here, right. So let's do today live interaction. Okay, PhD Tech, you're on air. Okay, go ahead.
Can we use exponential e power plus j omega t?
In the Fourier transform formula,
Can we use e power plus j omega t?
okay, let me write down the formula here. The basic formula for Fourier transform is shown here, where x of omega is equal to minus to plus infinity x of t e raised to minus j omega t dt, right. So you want to write, instead of e raised to minus j omega t, as e raised to plus j omega t.
Is that
Is that the
possible?
question?
Yes, sir. Is that possible?
Let me understand the question in its different flavors. Okay, first, if you see, what I have done is I have derived some kind of a relationship between Fourier series and Fourier transform, extending the idea of Fourier series to include Fourier transform, to include non-periodic or aperiodic signals, right. That is the first task I want you to remember. So when I do that, I end up with a relationship like this, right. So if you want me to be consistent with Fourier series, then I have to use here minus j omega t. Okay, but if you just want to know what happens if I write e raised to plus j omega instead of e raised to minus j omega, right, that's again an improper integral. It can be evaluated. Then I don't know what is its connection to Fourier series and Fourier transform, right. That's also something, but I will, when I come to discussing properties of Fourier transform, I will show you that that is the Fourier transform of x of minus t, right. X of t flipped, x of t real but flipped, right. So to be consistent with Fourier series, I have to define Fourier transform with a negative exponent here, otherwise I won't be consistent. Then whatever meaning I gave in Fourier series will not be carried over to this.
Thank you, sir.
Thank you. Okay, so there are some online chat questions. One is from BEC. It says Fourier transform of step signal. Okay, I will come back to that. I will come to, I know delta and u of t continue to haunt the students and continue to haunt the instructors, right. I have not talked about the existence conditions of Fourier transform. So let me first talk about the existence conditions, then take up these complicated things like u of t, right. So as a preview, I can say u of t is not a regular signal, right. I've said this thing in the past. Let me repeat it here today. U of t is not a regular signal, right. We are comfortable with energy signals because they are well behaved signals. they die down as they go towards infinity in both the directions. U of t is not like that. Okay, so strictly speaking, if you apply the existence conditions of Fourier transform, U of t should not have Fourier transform. But nevertheless, we take limits, and in the limit we assign a certain meaning of Fourier transform to U of t. Okay, this is not the class for that. I'm not talking about all Fourier transform. I'm restricting myself to use of Fourier transform in LTI systems. That's a frequency domain analysis, right? So I will not be getting into what is the Fourier transform of the step function, what is the Fourier transform of the signum function, and so on, right? The kind of stuff that is typically done in textbooks, but take that with a pinch of salt, because it is not your regular function. U of t is not a well behaved energy signal. Okay, so strictly speaking it should not have, but nevertheless we being engineers not concerned with mathematical niceties, we go ahead and do everything, right? But to a mathematician, he'll be wincing at this. I mean, to him it's horrifying that we do something like that, right? It has to be done through logic, it has to be done to be consistent with all previous definitions. So, but nevertheless we electrical engineers go ahead and define something to be the Fourier transform of a U of t, right? I'll stop at that because this is not a course on Fourier transform. Another question is, explain the concept of orthogonality in Fourier series, right? So let me then go back to Fourier series, and maybe I can erase this and talk about Fourier series. Let me go back and tell you what I did on the first time I talked about Fourier series. Is I said if x of t is periodic with period t naught, then its frequency is 1 by t naught hertz, right? And its radiance frequency is 2 pi f naught, or 2 pi by t naught radians per second. Okay, so if x of t is periodic, then Fourier series theory says this can be written as a naught a n cosine n omega naught t plus p n sine n omega naught t. Summation is over n equal to 1 to infinity, n equal to 1 to infinity. This is the first statement I made. Right? In that context, I said that cosine n omega naught t, n equal to 1, 2, 3, 4, okay, up to infinity. This is an orthogonal set, right? This is, so here I put cosine under brackets. It means I'm considering for all values of all positive values of n, 1, 2, 3, 4, like that. And so that entire set of functions is an orthogonal set. We now talk about what is orthogonal set. So it means if you take two elements from this set, such as cosine n omega naught t for one value of n, and cosine m omega naught t for another value of. So take two functions from this set, right? Call one as n, call one as m. It could be 2, it could be 3, right? Let's keep n and m distinct. And if you find the product, integrate over any one period, the claim is this will always be 0 for n not equal to m. As long as n and m are distinct, right? Any two functions taken from this set, when you find the product and integrate over one period, that integrates to 0. That's the definition of orthogonality. If two functions satisfy this definition, then they are said to be orthogonal. What is true for cosine is also true for sine. If you take a set of set of functions sine n omega naught t, that's also orthogonal. What is interesting is you can do one sine and one cosine. you can find the product of one cosine and one sine, this is also equal to 0. Here n can even be equal to m. So not only cosine set of equations, sine set of equations are also orthogonal. Sine and cos taken together are orthogonal. So to me, orthogonal simply means take the product of two signals from this set, integrate the product over any one period t naught. If that integrates to 0, then those two signals are orthogonal. Simple. Okay, and I'm saying many signals satisfy this property. Okay, so ask me if I not been very clear. There's a question from VCE. It says that's the one, right? What are the real time applications of Fourier transforms in finding out the spectrum, in finding out what frequencies are present, right? I will refer to the next couple of example and explain this in clearer terms. So Fourier transform tells me what frequencies are present in the signal. Remember, I am applying Fourier transform to non-periodic signals, right? So it is not very clear looking at the signal what frequencies are present, right? Lower frequencies, medium range frequencies, or high frequencies. So I would like to know what kind of frequencies are present in a given signal x of t. So big application of Fourier transform is in finding out what frequencies are present. I will come back to this question later on once again. Okay, so but for the time being, I'm going to stop it at that. The question from JNTU, it says impulse response is considered only for LTI systems, not for other systems. Why? A similar question was asked in the last class. They said, if I find the response of any signal to an impulse, is that impulse response? And at that time I had answered saying no. Only for LTI systems, the response to an impulse applied at t equal to 0, that output is called impulse response, because then I use that in the convolution. The output of an LTI system is convolution of input and the impulse response. So only in that context impulse response makes sense. Just because to any system I can apply an impulse at time t equal to 0 and get the output doesn't make it impulse response. I mean, so it's a technical definition, right? You can ask why not? I'm saying, in my definition, I'm going to call this as a dog, this as a cat. You can't ask me why not call dog as cat, right? I mean, that's a definition, right? In this case, only for LTI systems, when I apply an impulse at t equal to 0, whatever output I get is the impulse response, because then I can convolve that with any arbitrary input x of t to get an output y of t. Okay, so that's a definition, and that's it has a very strict meaning, and you can't stretch the meaning to mean anything. Okay, question from CITCMB, that's probably Coimbatore, so it's okay. Whether Dirichlet conditions satisfy non-periodic signals? Okay, good question. I still haven't done it. I'll come back and do it. Right, that's in the slides in the next couple of slides. When I ask the question, for what kind of signals Fourier transform exists? Previously, I had asked the question, for what kind of signals, for what kind of periodic signals Fourier series exists, and in response to that, I had said Dirichlet conditions, which are the signal should be an energy signal, it should have a finite number of maxima or minima, it should have finite number of discontinuities in any one period. Okay, that was the if a function satisfies these three conditions called the Dirichlet conditions, then a Fourier series for that exists, and the left hand side and right hand side, meaning this is the left hand side, this is the right hand side, they will be equal in the mean square sense. Okay, that's what we had to state for Fourier series. I'm going to make a similar statement for Fourier transform, but just wait for another 5-10 minutes. That's it. Okay. Well, I would really encourage more questions, because today is the last day. huh? Okay. So you know, what I have here is a proof, right? Or how do you apply Fourier transform to solve problems? So if e raised to minus 80 ut is a signal, then under certain conditions this integral is defined. This integral is defined. Okay, otherwise this infinite improper integral is not defined. So for this to be defined, a necessarily has to be larger than 0. Okay, so let's continue to that's what I said before to the question. When do we say Fourier transform exists? For what kind of x of t, right? Fourier transform exists. So the answer is the same Dirichlet conditions apply. Why? Why? Because we used Fourier series to derive Fourier transform, right? So to me, if the Fourier series is more fundamental, existence of that directly carry over to also Fourier transform. Okay, the way we derived Fourier transform is first making a signal periodic, then applying Fourier series, and Fourier series exists for any signal that satisfies Dirichlet conditions. So the same Dirichlet conditions apply. So meaning the signal has to be an energy signal. The signal should have only a finite number of maxima and minima. Signal should have only finite number of discontinuities. Okay, so those three conditions apply. If those apply, then Fourier transform exists. Okay, and by that definition, u of t is not an energy signal. Okay, so u of t, if we write a certain Fourier transform, it is by doing some tricks. Right? Straightforward, you cannot write Fourier transform to signals like u of t. Please understand this difference very clearly. This is something that mathematicians always warn us. We don't get that warning often, right? So heed to this warning. Fourier transform does not exist if you strictly go by Dirichlet conditions to signals like u of t. Okay, I can after another 10 minutes I'll make another stop and maybe we can have more discussions. So what is the interpretation? This was the question, right? Somebody asked, but not in the way of interpretation. They said, what are the applications? Right? And here I'm asking the question, what is the interpretation of Fourier transform? Right? When I say, well, let me erase this Fourier series and come back to Fourier transform. Write those two equations. So I have x of t to which Fourier transform exists, meaning Dirichlet conditions are satisfied. Then x of omega is x of t e raised to minus j n minus omega t dt improper integral, and x of t given x of omega is 1 by 2 pi x of omega e raised to plus j omega t d omega. Okay, so let me write these two equations. If you look at this second integral, what it says is x of t can be thought of as consisting of many complex exponentials, each of this value. It has infinite number of complex exponentials given by a certain amplitude, and they all combine, right? They all add together to make x of t a non-periodic signal. That's the interpretation. So let me read out what I've written here. X of t consists of infinite number of complex exponentials, right? Infinite number of complex exponentials, because omega goes from minus to plus infinity. So omega can take any value. Infinite number of complex exponentials, each of amplitude x of omega, right? And they are adding, meaning integration is addition. They add to make x of t 0 outside a certain domain. In this case, I have written t belonging to a and b, right? A and b can be infinity, plus minus infinity. Right? A and b can be any value. All that I'm saying is x of t is not periodic, right? So it is just one period, and so it is 0 everywhere. It could be time limited, defined only between a and b, or defined between minus to plus infinity, doesn't matter. So that's the interpretation. So I'm saying x of t consists of large number, infinite number of complex exponentials. Each complex exponential has a certain amplitude and so on, and they all add together, right, in a vectorial sense. So now let me take simple examples, right, simple examples to see what kind of results we get, and we interpret now the Fourier transform. Since the question was what does Fourier transform mean, so let's take some signals x of t, compute the Fourier transform using these two equations, and then let's see what can be the interpretation. So I've taken x of t in this case to be defined between minus half and plus half, and is 0 beyond this and beyond this, and between minus half and plus half its value is equal to 1. This kind of a signal is called a rect, right, in textbooks on signals and systems, in communication and so on. Since we are now interested in defining new and new terms, right, often confusing terms, this is defined as a rect. So when I say x is a rect, it means time, it occupies a time duration of 1 unit, in this case between minus half and plus half, symmetric about the origin, okay, and its value is equal to 1. That's a rect. So we want to find its Fourier transform, right. I will not go into the mathematics of that, meaning I take this equation, substitute x of t equal to 1 between minus half and plus half, and carry out this integration. You can do it, right, just go home and do it, nothing great, not rocket science, simple stuff, right. If x of t is rect, then this value is equal to 1 between minus half and plus half. For all other values it is 0. So carry out this integration, right, nothing great. So I have carried out the integration, right, skipping many steps which I want you to go home and fill it up, and claim that the Fourier transform of x of t when it is rect is given by x of omega given by sine omega by 2 by omega by 2. It's in the form of sine theta by theta, sine omega by 2 by omega by 2. I want you to go home and show this. And if you see in this particular case, x of omega is real. Remember, some time ago I claimed that even when x of t is real, x of omega can be complex. When it is complex, I have to sketch its magnitude and its phase and all that. But in this case, fortunately, x of t is real, x of omega is also real, because it's only sine omega by 2 by omega by 2. It's sine theta by theta form, and you know that sine theta by theta, as theta approaches 0, is equal to 1. So I can now go ahead and sketch this function. So which is what I've tried to do. So I've sketched this function, and omega can take values from minus to plus infinity. So when it takes very large values, denominator becomes very large, numerator, because it is sine theta, considered to be between minus 1 and plus 1. So numerator is bounded, denominator goes on increasing unboundedly, so it goes to 0. That's what is shown here. So the function x of omega becomes 0 as you go away from origin. So this is a sketch of x of omega for negative and positive frequency, and you can see that even this x of omega has an even symmetry. You replace omega by minus omega, sine of minus theta is minus sine theta, that minus and the denominator minus get cancelled, and you get back the same form. So this is an even function, x of omega is even. That's clear even from here, right. About the y axis, both sides are even. Replace omega by minus omega, you get the same value. The interpretation here is this x of omega contains significant contribution of low frequencies, because in low frequencies its value is very high, and high frequencies away from 0 it becomes very small. The rect function contains low frequencies and does not contain high frequencies. That's one interpretation. So in the previous slide I said Fourier transform means that x of t consists of complex exponentials of certain amplitude. In this particular example, it contains complex exponentials of lower frequency, of frequency around origin, right. they are more dominant than the frequencies away from the origin, because you see here the values around origin are bigger, the values away from origin are small. So that's the idea of this. I can now talk about x of t. What if x of t is delta of t? The question was asked, what if x of t is u of t, and I had said u of t is not a regular function, so let's not talk too much about that. Similarly, x of t delta t also is not a regular function, right? So how can you talk about this? How can you talk about Fourier transform for this? So my question is, you look at this x of t, right? Its area is equal to 1, right? Its width is 1, height is 1, so its area is 1. Okay. Now keep the area constant, reduce its width, meaning if you bring it down by a factor of 2, height increase by a factor of 2 to keep the area equal to 1. If that happens, then the point where they first cross 0, that's here and here, they move further apart by a factor of 2. You again bring it down by a factor of 2, increase the height by a factor of 2. So if you go on pressing the signal from both the directions in x of t, the height goes on increasing. So you are squeezing it and the height is increasing in time domain, in the frequency domain, right? The point where it first becomes 0 moves away from origin, goes further and further away, right? In the limit where the two sides are completely squeezed, height is very large, what happens to this point? Where does this point go? Right? Where does this point go? This point keeps moving away and away and away. Finally, it goes to infinity. When it goes to infinity, the function has this shape. It's constant because it is not going down. It's constant. So when the x of t gets squeezed, then x of omega becomes constant at 1. That's what I've tried to show here. Right? When x of t becomes a delta, x of omega is equal to 1 for all frequencies. Remember, the way I have argued is in the limits. I didn't just put in delta of t in this equation, and because x of t cannot be integrated like that. Okay, so it's always for u of t and delta of t, you see that you are applying the limits and arguing your answer. Okay, do not treat u of t and delta of t as your regular functions. In my argument, if x of t approaches delta of t, then x of omega approaches 1 for all frequencies, because then it's flat. So now the moment I define this, several ideas fall in place, right? I will not get into all those ideas, I'll just state the result. Okay. Instead of x of t becoming delta of t, what if x of omega is delta of omega? What if I have an impulse in the frequency domain? Right? You can argue, right? The time domain will be constant, but because there is a 2 pi there, right? X of t will be 1 by 2 pi. Okay. Another way of stating this is, if x of omega is 2 pi delta omega, if you bring in 2 pi here, then its Fourier transform or inverse Fourier transform x of t will be 1 for all times t. If you don't include this, then it will become 1 by 2 pi. If you include 2 pi here, then this will become 1 here. Okay, because there is a 2 pi difference between this integral and this integral. That's what shows up, there. So I will not, discuss this result anymore. If x of omega is an impulse, x of t is constant function. By the same logic, if you delay this, if instead of this, if x of omega is now shifted impulse, if it is a shifted impulse, right, turns out that x of t is e raised to j omega naught t for all times. So this is the complex exponential, everlasting exponential. You get interesting results. If x of omega is an impulse, then x of t is a constant. If x of omega is a shifted impulse, x of t will be a complex exponential. Okay, and you can now apply all kinds of results, right? You can say what if my x of t is cosine omega naught t, right? You can use Euler's formula, write this as e to the power of j omega naught t by 2 plus e raised to minus j omega naught t by 2 and take individual Fourier transforms, right. So for this it is half into 2 pi delta omega minus omega naught, and for this it is half 2 pi delta omega plus omega naught. Okay, half and half cancel out and you get what I've written there, which is pi delta minus omega naught plus delta omega plus. You have two impulses, one impulse at omega naught, one impulse at minus omega naught of height given by pi. Okay, so that's a consequence. Once you understand the rect and its Fourier transform, then argue based on limits. As you squeeze x of t, x of omega becomes wider and wider and wider, eventually becoming, you know, a constant function. That's the, limiting argument. And once you understand that, all other ideas, all other answers simply fall in line. Okay. So now I think I'll again pause and ask questions. We'll come back to this. I mean, I'm not going to discuss too much of Fourier transform because it will take me away from LTI systems. But nevertheless, I think it's a good point to pause and seek questions. There's a question from PSG Tech that says, periodic signals are power signals. Yes, the answer is yes. Periodic signals are power signals, right? Square integrable, right? So, when you integrate them over a period, you can integrate them, but if you integrate over the entire length, you cannot, because periodic signals don't go towards 0 as t increases in both the directions. So, periodic signals are power signals, correct. From SCEKL, what is the Fourier transform of a periodic signal with discontinuity? Fourier series with discontinuity, right? Interesting question, because we have done this before. I think I'll also make this question a little bit different. So let's take a rectangular function, periodic. Let's take it as this is t naught by 2 minus this is t naught by 2 plus. This is one period. This. Okay. Does it have discontinuities? If you see here, discontinuity. Okay. So this has discontinuities. If you take a triangular periodic signal, it has discontinuities. Nevertheless, we went ahead and computed Fourier series for this because this is periodic. I also argued that it doesn't converge to this function everywhere, right? And at these discontinuities, they converge to the midpoint, and the right hand side doesn't converge to left hand side everywhere. I in fact took example where I had taken 2 terms and 3 terms and 20 terms of the summation and showed that it leads to what is called the Gibbs phenomena, right? So the answer is, if there are discontinuities, you can still go ahead and compute Fourier series, but the two sides, the left hand side and the right hand side, are not equal everywhere. It doesn't converge. Right hand side doesn't converge to these values everywhere. Okay. So the convergence has to be understood in the mean square sense. So it's a more complex mathematical explanation, but nevertheless at our level, meaning for the second year, third year engineering level, you can say go ahead and compute Fourier series for any periodic signal for which which satisfy Dirichlet conditions. This only has 2 discontinuities, so it satisfies Dirichlet conditions. Dirichlet says it cannot have infinite number of discontinuities. It only has 2 discontinuities, so it's okay. From PSG Tech, can we apply for Fourier transform for periodic signals? If so, what is the need for that when there is Fourier series? Very good question. I mean, there is no need. I mean, I can see where the question is coming from. Often in textbooks, right? All kinds of for all kinds of functions, we find Fourier transform, right. That comes from what I did here, which is I extended the idea of Fourier transform to include delta function, to include the impulse function. I said if you take the limit, then you can apply Fourier transform and get the Fourier transform of an impulse function. So the moment I do that, all kinds of functions open up, right? Just like I said, if x of t is e raised to j omega naught t, then its Fourier transform is 2 pi delta omega minus omega naught. So if that is true for one exponential, if I have series of exponential, which is what the Fourier series is, then for each term I can apply Fourier transform, right? So by the moment I extend Fourier transform to include delta function, then that answers your question, right? I mean, there is really no need. There is really no need, right? Because why do I do Fourier transform? I want to find out its spectrum, but Fourier series also already gives me that information, right? So there is no need. But for some mathematical operation, it might be required, like things like sampling and all. I think it might be required, right? But if you are just trying to find out the spectrum, then Fourier series gives you all the information you need. You don't need to do Fourier transform. How to find the Fourier transform of periodic impulse train? Oh, it's given in all the books. I mean, it's given. I mean, you can do it. The way to the question is given a periodic impulse train, what is called the comb function. Comb is thing that you use to brush your hair. How do you find Fourier transform? Right. I think it's given in all the textbooks. Standard trick is because a periodic impulse train is periodic, you write its Fourier series, right? And so when you write its Fourier series, it is xn e raised to j n omega naught t, and you take e raised to j n omega naught t, take its transform in the form of 2 pi delta omega minus n omega naught, right? And so you could write Fourier transform for impulse train. I mean, not a big deal, but I want you to express caution because it involves delta, right? And delta is not your regular function. So even though textbooks do all that, to me it is I tend to take it with a pinch of salt, right? It is mathematically not rigorous. Even if you do it, please hide it from mathematicians because they will be horrified. They are not used to doing such operations, right? So engineers can do whatever. It may or may not make sense, but mathematicians are much more careful, right? So by with that caution, I can say, as engineer, you can go ahead and compute Fourier transform of periodic impulse train. Question again from PhD Tech: can we use Fourier transform for analyzing a system? I'm going to do that. In fact, that's the reason why I'm doing Fourier transform, right? So I'm going to come back and do it. Question is, what are the real-time applications of Fourier transforms? We have not answered the question fully. I will take it up again. I've simply done some hand waving and said, it tells you to find, it tells you what frequencies are present. So let's keep it at that. Maybe in the next half an hour, I'm going to come back and answer that question. From SITH, the question is, what is the nature of spectrum of bipolar NRZ signal? Oh God. Okay. So okay. So this is going too far away from what I'm doing here, right? So what is an NRZ signal? So you consider random bit stream that's coming to you, some electronic message. Let's say as a form of 110000 111 and so on. So some arbitrary combination of ones and zeros are coming to you. You represent one as high for the entire duration and another one as high for the entire duration, 0 as negative for the duration, 0 as another negative, and 0 as negative, right? Then 1 and then 1 and 1. So this is what is called the non-return to 0, meaning during the bit interval the signal doesn't go to 0. Signal stays either positive high or it stays negative high. So this is the non-return to 0 signal. Bipolar because it has two values, right? A plus high and a negative high. So this is the NRZ signal. The question is, how do you find its Fourier transform? That's required for the spectrum. Okay, that's required for the spectrum, and the complicated arguments. Okay, and the uh, uh, arguments finally say that is something like 1 by T naught into x of f magnitude square, where T naught is a bit period and x of f is the signal shape used. In this case, the signal shape used is a rectangular pulse that is on for T naught seconds, right? And its height is equal to 1. This is x of t. So this pulse is used in NRZ signal. If it is plus 1 as it is, minus 1 it's ulta. Right? You flip it and use it here. So if you find its Fourier transform x of omega, well I wrote here omega, f, sorry, I'll write it as omega. You find its x of omega, take magnitude square, that is the spectrum of the bipolar NRZ signal. Okay, more than that I cannot tell you at this moment, but you can, many books on communication such as Proakis and all, they derive the result, and result is quite simple. Okay, it comes from certain ideas of a cyclostationary process, and you have to make cyclostationary process stationary and all that. So it takes me too far away from what I'm doing in this class. Okay, so because the problem is not of general interest, I'm not going to spend time on that. So I continue slides. Okay, so what are the questions? What are the properties? I mean, since I have the Fourier transform, I define Fourier transform. Um, if you read any textbook on Fourier transform, it has lots and lots of properties, right? I mean, when we talk about signals and systems, we typically spend more than 2 weeks discussing lots and lots of properties. Remember, Fourier transform is nearly 150 years old. Lots of people have discovered lots of interesting properties, so we make you read all those properties, right? So I just listed the properties here. One is linearity, meaning if there are two signals x1, x2, each has a Fourier transform. The summation of that, its Fourier transform is a summation of the individual Fourier transform. So, simple things like that comes from integration operation itself. Then the second property I've listed here is conjugation and conjugate symmetry. So what it means is, if x of t is real, then its Fourier transform has conjugate symmetry. Its magnitude is even symmetric, its phase is odd symmetric. Let me take you back to the example I had shown here, right? So this is where I had x of t as real. I considered x of t as real. This is its magnitude, this is its phase. Its magnitude, its magnitude is even symmetric, its phase is odd symmetric, right? So that's what the conjugate symmetry is about. It's that's a conjugate symmetry property. Then there is a scaling operation. I can do time scaling and frequency scaling. So if you remember what I had done in the past, if you compress in time, the frequencies expand. If you compress in frequency, then the time expands. So the time and frequency scaling, again, thank you. So can be a property of that. I'm not going to get into all those 1,000 properties of Fourier transform. Then there is time shifting and frequency shifting. Frequency shifting operation becomes modulation. Time shifting operation becomes a change in phase. So with lots of applications in communication, right? Those of you who take communication systems course, you would have seen some of these properties. Then there's an interesting property called duality. Again, without getting into too much of detail, right? Let me write x of omega here, definition, which is x of t e raised to minus j omega t dt minus plus infinity, and x of t as 1 by 2 pi minus plus infinity x of omega e raised to plus j omega t omega. So if you look at these two improper integrals, They kind of seem similar. Take the function, multiply this with e raised to minus j omega t and integrate from minus to plus infinity. There are some minor differences here, the sign is negative, here the sign is positive, here the scaling is 1, here the scaling is 1 by 2 pi. Other than this, it's obvious that both are improper integrals, more or less similar, right? And that is the reason for duality, right? What happens in the frequency domain has a certain effect in time domain, and if the same phenomena happens in time domain, has an equivalent effect in the frequency domain, right? So that's the idea of duality. Because of which you can say, if you compress in time, frequency expands, or if you compress in frequency, time expands, right? And so that's a duality because of this plus minus nature here. Interesting things happen. And typically textbooks spend a lot of time discussing those properties, but I will not spend time here. The next property is what I've shown in red is convolution, right? That is the property of interest to us, okay, because we are talking about linear time invariant systems. What it says here is, if you have an LTI system with input x of t and impulse response h of t, output y of t, then y of t is given by x convolved with h of t, or x of tau h of t minus tau t tau, or h of tau x of t plus tau t tau. So this is the various forms of writing the same convolution, right? This is all well known and we've written this, and hopefully you have done the homeworks, and so you know that doing convolution is not easy. I mean, you take one function, flip it, take it to minus infinity, slowly drag it. I mean, all kinds of complicated things you have to do to compute convolution. Not a very pretty idea, right? So what the convolution property says is, you find its individual Fourier transform, assuming they exist. If x of t, you take Fourier transform, call it as x of omega. Take h of t, find its Fourier transform h of omega. Then the product, right? Then y of omega is simply x of omega by h of omega. Just simple multiplication, right? I mean, we are happy with multiplication. No convolution, no complicated, take the signal, flip it, take it to infinity and drag it, none of that complicated things. Simply take individual Fourier transform, find the product, that is the Fourier transform of the result of the output. Now, knowing y of omega, I can get y of t by this inverse Fourier transform relationship. X of t, find x of omega, h of t, find h of omega, find the product, that's the Fourier transform of the output, then apply inverse to get y of t. So convolution property is most widely used to avoid doing convolution. It replaces convolution by simple multiplication. That's the application of this. Then there are other properties like differentiation and integration. This is not a course on that, so I'll skip. I'll simply mention lots of properties exist, right? So now I'm going to focus only on convolution, because that takes me back to what I'm doing in this course, which is LTI systems, frequency domain analysis, right? So basically what I've done here is what I've already I've already explained all this here. And see, we know that the input output of an LTI system are connected by convolution operation. Y of t is x convolved with h. In frequency domain, convolution is replaced by multiplication, right? And so y omega is x omega into h omega. So convolution becomes extremely simple operation of multiplication, and so we are happy. That's one reason why we go into the frequency domain, because time domain is complex. Okay, so we have two domains then. This I call as the time domain, this I call the frequency domain. I can go, because the operations are completely reversible, either I have time domain going to frequency domain, or I have frequency domain going to time domain. So I can go. So I now have another tool, another good way of solving problems. So I can work in the frequency domain and don't do multiplication, don't do convolution, but only do multiplication. And here is an example of that. This is something that we had solved before. So, let me come back to this problem and solve this. So, in this case, I have an LTI system. X of t is given by e raised to minus t u of t. Some example, okay, and h of t is e raised to minus 2t u of t. I had solved this problem long time ago when we talked about convolution. I am revisiting that problem, and I want you to remember the result I had for Fourier transform example. So, for this x of omega is 1 by 1 plus j omega. Remember, it was e raised to minus at ut, the example I had given, it was 1 by a plus j omega. Here a is 1. So, Fourier transform of this is 1 by 1 plus j omega. Similarly, for this, it is 1 by 2 plus j omega. Given x and h, computing the Fourier transform is piece of cake. Simple, extremely simple. So, in this case, I know x of omega, I know j of omega. So, resulting y of omega will be 1 by 1 plus j omega, then 1 by 2 plus j omega. For this particular example, I am stuck, right? I don't have now, if you carry out the multiplication, you are dead, right? It's 1 here, then minus omega square and plus j omega plus 3 j omega, and difficult things. Problem gets really complex. Instead, if you do partial fraction expansion, 1 plus j omega minus 1 by 2 plus j omega. If you do partial fraction expansion, you will see that denominator is same, numerator is j omega cancel each other, 2 minus 1 is 1, so it is correct. You'll ask, how did I do this? I mean, it comes out of solving many problems, right? It's a simple experience you gain with time. Students might be confused on day one, but if you repeatedly solve problems, you'll become more and more confident, right? That's the reason why we give problem solving. So, the moment I have partial fraction expansion, I use the linear property of Fourier transform, find the inverse of this, find the inverse of this. So, if we do that, then this inverse is e raised to minus t, this inverse is e raised to minus 2t u of t. This is exactly the result we had got long time ago. If you remember, some 2 or 3 classes before, I had solved convolution for the same problem in the convolution domain, right, by taking the signal and flipping it and so on. So, that is what exactly what I have tried to do, right. And if you sketch this, if you sketch y of t, remember the picture I had shown, this is my x of t and this is my h of t. It is falling more rapidly because it is e raised to minus 2t. If you sketch this, this function becomes like this. At t equal to 0, it is 0. At t infinity, it is 0. In between, it takes some values. Remember, you can go back and look at my slides. Some 2 or 3 classes before, I had solved the same problem and sketched it. Okay. So, I'll give one interpretation and then we take a break for questions. So, no, not right now, after this slide. So, now I have done time domain analysis and frequency domain analysis. I have done everything in convolution. For LTI, I have done now as a product in the case of Fourier transform, right. So, how do the two things match? One I am going to call as the time domain, other I am going to call as the frequency domain. So, here I have 2 columns, left side I have time domain, right side I have frequency domain. So, in time domain, if my input to the LTI system is delta, as here, if my input is delta, then the output y of an LTI system is called impulse response h of t. Okay. Equivalently in frequency domain, if input is a complex exponential, output is a scaled complex exponential because of eigenfunction property. Okay, so that's the starting point in time domain and in frequency domain. Then we continue. In time domain, I can express x of t as consisting of scaled and shifted deltas given by this integral here. X of t is shown by scaled and shifted deltas, and so y of t will be scaled and shifted impulse response h of t. So y of t is sum of scaled and shifted impulse responses. This was the time domain result. In the frequency domain, I am writing x of t as consisting of many complex exponentials e raised to j omega t's, each with different amplitude given by x of omega, and output is this complex exponential remains as it is from eigenfunction idea, amplitude remains as it is, there is a gain. For each frequency, I have h of j omega as the gain. That's a scaling. So y of t output is given by this integral. I have a time domain result, I have a frequency domain result. Both are analogous to each other. One consists of convolution, one in terms of multiplication. So here I'm convolving x and h. Here I'm multiplying capital X and capital H. So impulse and complex exponentials are we showed that if the signal is uh, complex exponential, its Fourier transform is a delta, or if the signal is a shifted delta, its Fourier transform is a complex exponential. Right? So because they are dual of each other, I can put down time domain and frequency domain analysis next to each other and compare what's happening, and there are analogous results happening. Okay, so with this, I take a break now. 10 minutes of question answer, then we start the final part of the talk. Right. So now I really want all of you to ask questions. Think about this and ask me questions. So there are good questions here. The question from PECTN. It says, what is the condition for stability of an LTI system in frequency domain? Okay, good question. So we said the condition for stability in time domain is that the impulse response h of t of an LTI system should be absolutely integrable. Okay, so the condition for stability was this was the condition for stability. This integral should exist, should not blow up. Okay, the impulse response should be absolutely integrable, and that is the condition for a Fourier existence of Fourier transform. So the condition for stability for Fourier transform is if the impulse response has a Fourier transform, the system is stable. Simple, excellent, very simple answer. If this impulse response has a Fourier transform, then the system is stable. Okay, is DC signal periodic or non-periodic signal? Difficult question, right? Well, DC signal is it is constant, it has no frequency, or its frequency is 0. So it is a degenerate signal if you think of it as a periodic signal, because you can assign any periodicity to it. Its periodicity is 0, right? I mean, it's so you can say it repeats with this T naught, that T naught, and so on. So you can assign any. So it's a degenerate periodic signal. I mean, it's only DC signal, right? So after all, what can you say? DC has all frequencies. Please tell the difference between sampling function and a sinc function representing the spectrum of a rect pulse. I don't quite understand what is a sampling function and what is a rect function. Let me answer to the best of my ability, because I'm not very sure what the question is. So in the textbooks, if they want to sample a signal x of t, right, they multiply this with a train of impulses. Train of impulses. So wherever the impulse occurs, that value is picked up because of the shifting property. This picks out one value, this picks out one value, and so on. Right? This is 0, t, 2t, and so on. Okay. So this is the this is how sampling is explained in textbooks. Okay. So you know that I've been arguing in this course for the last 5-6 lectures. Impulse is not your regular function. You cannot generate an impulse in the lab, right? Instead, if you multiply with a periodic signal like this is something that you can generate in the lab, right? This is called the duty cycle. This is the on time, this is the off time. On time is very short compared to off time. So it has a certain duty cycle. When off time, on times are equal, it is 100% duty cycle, right? And here the on time is much smaller compared to off time, so it has a very small duty cycle. This is something that you can generate. You know, when you next go to electronics lab, look at the signal generator, right, and try to generate a signal like this where you can control the duty cycle. So instead of multiplying x of t with a train of impulses, it's possible to do this, and you can argue that this also leads to sampling. This also leads to sampling. There could be some small differences between this and this, but the general result of sampling, that of aliasing, spectrum overlapping, and so on, happens even with this. So you could take this and rederive the sampling results, right? So this is much more realistic, something that you can do it in the lab, right? So apply the same tools given in the textbook for this train of impulses for a rectangular pulses, and sampling could also be thought of as multiplying x of t with this. Okay, so that's my answer to that question from PhD Tech. It says, what is the impulse response of a differentiator whose output y is dx by dt? Okay, so one of those textbook kind of questions, but let's see. What it says is I have x of t at the input, and we said the derivative is, and output is y of t. So y of t is dx by dt. If you take its Fourier transform, then this is y of omega, this is j of omega into x of omega. So derivative is j omega or j2 pi omega. I mean, I forget what it is, but this can be shown. This can be shown, right? Without any problem. I mean, the way we show this is we start from the first principles. X of t is x of omega, 1 by 2 pi, and e raised to j omega t d omega minus or plus infinity. Right? Differentiate both the sides, dx by dt, and interchange the order of integration and differentiation. So this is going to be x of omega. X of omega is not a function of time, so it comes out. This is j omega e raised to j omega t d omega. So that's equal to 1 by 2 pi minus or plus infinity x of omega j omega e raised to j omega t d omega, and x of t is y of t. So this is y of t. So you know that y of t, right? So this is the first function. This is the second function. So h of omega should be j of omega. That's how it is derived in textbooks. I mean, quite easy to show this, right? It's sort of more interesting thing is, what does it mean? I mean, if you say h of omega is j omega, if you look at its magnitude and phase, right? Its magnitude is something like this, right? Sorry. Wrong. I sketched 1 by omega. Its magnitude is something like this, right? H of omega is, remove j, it's omega, positive, omega this way. This is the magnitude plot. How about the phase? How about the phase? When omega is positive, right? Omega is positive, it is j. When omega is negative, it is minus j. Right? Plus j is 90 pi by 2, and it is minus 90 minus pi by 2. So you can plot the magnitude and phase response, and because the derivative is still a input is real, output is real, so this has a symmetric conjugate symmetry, right? And so that there are many ways of deriving this same result, and I've shown you one method. From BEC, what is the relationship between eigenvalue and eigenfunction of the system? I said complex exponentials are eigenfunctions of LTI system. So the question is, what is the relationship between eigenvalue and eigenfunction? Okay, so let me answer that question in a slightly different way. Okay, so let me take a matrix A given by a 2 by 2 matrix 1 2. I've taken some arbitrary matrix 2 1 1 2, right? And let me take xy plane xy, right? And let me take a point here, point x, which is 1 and 2. I have a vector here, I have a point here whose coordinates are 1 and 2. Let me transform this point by this matrix, typically called let me find out a vector y by transforming A, right? By taking this point and multiplying with the matrix A, which transforms it. So let me do that operation. 2 1 1 2 and x is 1 2, right? If you carry out the matrix operations, I don't know if I'm very good at that. 2 into 1 is 2, so this is 4, then this is 1, and so it's 4 and 5, right? 4 and 5, 1 and 2, 1 2 3 4, 1 2 3 4, so it's over here. So this was my point 1 2, this is the point 4 5. Okay, so what I want you to understand is, when I transform a point in xy space by a two-dimensional matrix, two things happen, right? This vector changes its direction. It was in this direction, now it is in this direction, so its direction is changed. This was a value, this was its value, so it's both transformed and rotated. This point moves to this, and its angle also changed. So when you apply a transformation by a matrix to points in n-dimensional space, they usually undergo rotation and translation, right? This point has moved here, this direction has changed here. This is the normal behavior. Now let me try this on a vector. Let me take a vector x whose value is 1 1. I've taken a vector here value 1 2. Let me take a vector value 1 1. Let me apply the transformation on this vector, right? 1 1 is 1 and 1, point somewhere here. Okay, 1 1 is somewhere here. Okay, so if you apply the transformation 2 1 1 2 1 1, tell me what happens. 2 into 1, 1 into 1 is 3, 1 into 1, 2 into 1 is 3. So this is 3 1 1. So this is in the same direction. 1 1 was here, 3 3 is here in the same direction, same 45 degrees. So this particular vector did not undergo a change in the orientation, because 1 1 was an eigenvector of this. Please go home and show this. 1 1 is an eigenvector of this, and 3 is the eigenvalue of this. Okay, so eigenvalue, eigenvector means a particular vector for a transformation matrix A, results in no change in the direction just results in scaling. That's eigen vector eigenvalue for a matrix A. Identically, for an LTI system, if I input e raised to j omega t, I get the same function at the output. If I multiply 1 1, I get 1 1 at the output with some scaling factor. This is some scaling factor. Same result happens here. So by there is a isomorphism between eigenfunctions and eigenvectors. E to the power j omega t are like eigenvectors of a matrix. These are eigenfunctions of an LTI system, because the same thing comes out. 1 1 comes out here. So it's based on that we have this idea called eigenfunctions. From BEC, can we determine whether the system is LTI or not, given the response of input is other than unit impulse? Your arguments are circular, right? Let's break it down. Right? Given a system, if it satisfies homogeneity, additivity, then it is linear. Given a system, a delayed input results in a delayed output by the same amount, it is time invariant. If the system has these two properties, then I call the system as LTI. And to LTI system, if I give impulse as input, whatever is the response, I call it as the impulse response, right? Let's go linearly. Let's not get into a circular definition. If some other thing is given, can I find impulse response and so on? No, no, no. First, is the system linear? Is the system time invariant? Then can I give input delta of t at t equal to 0? What is the output? That is impulse response. So we have to satisfy condition 1, 2 and 3 to arrive at impulse response. And you probably can find different ways, but you will have to justify calling it impulse response. Question from SITH: why is the sinc function used to approximate delta function? I did not use sinc function to approximate delta function, right? What I said was, there is a rect, it has its Fourier transform in the form of a sinc function. Sinc means sin pi t by pi t. In electrical engineering, sinc of t means sin pi t by pi t. This is our definition. The reason, the arguments I made were the following: if x of t is a rect function, then its Fourier transform is sin omega by 2 by omega by 2, something similar to this. Okay. And I sketched that. Then I applied the limiting argument. Let me squeeze x of t in the time axis, keeping the area constant to 1. Okay. When I do that, the first time when this sin omega by omega goes to 0 becomes wider and wider and wider. In the limit, it goes to infinity, meaning that sinc function became constant, equal to 1. That's the limiting argument I used to find the impulse response of to find the Fourier transform of an impulse function, right? I didn't say sinc and so on. So I didn't use sinc as an approximation to a rect. I used a limiting argument on that. Okay, she says I did not answer these questions from VCE. What are the real-time applications of Fourier transforms? To find what frequencies are present in the signal, right? Like a spectrum analyzer, or a spectrogram. Oftentimes we want to find out what frequencies are present. Low frequencies, high frequencies, medium frequencies, right? In communication, we are always interested in what are the frequencies present in the signal. So Fourier transform helps us in finding out what frequencies are present. So that's one big application. The second application is whether Dirichlet conditions satisfy non-periodic signals. I said yes. Just after this question was asked, a couple of slides later, Dirichlet conditions came. I explained this one, right? So I'm done with this. Okay. So after this, I think we have come to the end of this now. So the last slide is energy spectrum, right? There's a Parseval's condition, Parseval's theorem that says that if I have an energy signal x of t, then Ex is given by x square of t dt, assuming x is real, assuming x is real. Say you can show that this is equal to 1 by 2 pi x of omega magnitude square, because x of omega can be complex, we look at its magnitude, and d omega from minus to plus infinity. So this relates energy in time domain with energy in the frequency domain. This is the Dirichlet condition, sorry, this is the Parseval's theorem, and the function x of omega magnitude square is called the energy spectrum. What it means is, let's say this is x of omega magnitude square, given any frequency omega 1 to omega 2, it tells you how much energy is present in that particular band, right? And so in that sense it's the spectrum, right? Given any frequency, you can specify a pair of frequencies, you can tell us what is the energy in that band. So this is the energy spectral density function x omega square, right? Oftentimes we are interested in computing the energy spectrum of a signal, of an energy signal x of t, right? Because from Parseval's we can find out the energy of that. Okay. So if you recall, we had started off with the energy signal long time ago. We are ending the lecture with Parseval's theorem that computes energy in time domain and relates that to energy in the frequency domain, and this is the energy spectral density function x omega magnitude square. So with that I conclude. I think I have no more slides left, so I've come to the end of this. So we started off with the convolution, LTI systems, that was the time domain, and then we went to frequency domain. We talked about Fourier series for periodic signals. We extended the idea of periodic signals to include aperiodic signals, and also then talked about Fourier transform, right? So I've done all that in a very short time, meaning in 4 sessions of 2 hours each, 8 hours. So it's extremely short time. Typically it occupies half a semester of 20 to 25 lectures. So I have compressed many things, I've gone over a certain things very fast, I've skipped a few things, right? So given all that, I've tried to give a picture of why a Fourier series and Fourier transforms are important in the study of LTI systems, given the fact that we have eigenfunctions result for LTI system. So I think with that I conclude. I have last 2-3 minutes, so maybe I can do a session with some college. CITC. Yes sir, hello.
No, sir, from CIT, feedback from these 3 sessions regarding the linear time variant systems and
Okay.
periodic applied systems, including concept of control systems, are very useful, sir. And your
Yes.
lectures are very important and useful for us. And we are expecting more in the future, like these classes, and more sessions we are expecting, sir. We learned a lot from your lecturers, sir. Thanks a lot, sir.
Okay, thank you. So okay, some questions are there. How to find energy spectrum in MATLAB? Okay, so you know, for that you have to understand many things. First is that MATLAB is a discrete time system, right? If your signal is x of t, which is continuous time, MATLAB cannot handle that. MATLAB can only handle discrete time. Okay, so you go from continuous to discrete time by taking samples. So when you take samples, if you look at the mathematics, what happens in the frequency domain, the sampling period acts as a scaling factor. So you need to keep track of that. Then you find energy, right, of the signal in continuous time, and see what happens to that in the frequency domain. So it's possible to do all that, but you have to do it with care, right? You write down all the formulas one below the other and see what happens. Only after that go to MATLAB. Don't just go to MATLAB and do whatever FFT or something, because MATLAB has a command for that. It's meaningless, right? So first put down all the relations that you understand from continuous to discrete time step by step, then write the energy, and only then you go and compute that in MATLAB. Okay, so don't jump and go to MATLAB because you have a laptop and in which MATLAB is loaded. Very risky operation, right? So all I say is do it with caution. We use Laplace transforms for analysis of a system. Why? Okay, so good question. So Laplace transform is a generalization of Fourier transform. Fourier transform, we take the integral x of t with e raised to minus j omega t. In Laplace transform, we take it as e raised to minus st. S is the complex frequency which we discussed in the class. So it's a more general transformation. So what is true for Fourier transform is also true for Laplace transform. So many of the results come out even easier in Laplace transform. So you could analyze in the frequency domain with j omega axis, or you could analyze in complex frequency domain with the sigma plus j omega axis. So Fourier transform and Laplace transform are very close to each other. Okay, so I have Vasavi College for live interaction. Please go ahead.
Good afternoon, sir.
Good afternoon.
Thank you, sir. For finding the solution for the signals, that is for analyzing the signals.
Yeah, I mean it's possible to work out in a time domain completely, right? There is a state space method and so on. So LTI systems assume that initial conditions are 0. So what if the initial conditions are non-zero? So there is this entire thing of state space which is very elegant, right? So many computer applications use state space and not use transform methods, right? But that's derived from partially from our understanding of convolution, right? So you could stay and do entire thing in time domain. You don't have to go into the frequency domain at all, right? Sometimes going to frequency domain makes your life easier. That's the reason why you might want to go to frequency domain, right? If two systems are cascaded, then there's an impulse response is convolved. Why? We talked about this long time ago, right? When we talked about cascading of two systems. Uh, what is the physical significance of power spectrum density function? Nothing other than it gives you a way of knowing how the frequencies are distributed across. I mean, how the energy is distributed across multiple frequencies, right? It tells you whether it's frequencies are in the low frequencies or in the high frequencies and so on. Why there is no ROC in Fourier transform? Because we have only one omega, so if you look at the complex plane, that's complex frequency. So here there is just one line. So either the Fourier transform exists or it doesn't exist. I mean, like, there's no ROC there, right? So we're operating in a just as one straight line in the complex plane. So how can you have any ROC there? Orthogonal property be applied to Fourier transform. Depends on what property you are applying to. I mean, what is your application, right? Not very clear to me. If two LTI systems are cascaded, then the impulse response is convolved. Okay, fine. Already talked about how the periodicity of the signal wave is calculated. I mean, we define periodicity by simply saying that if x of t is equal to x of t minus t plus t naught for all t, meaning a signal and its shifted versions look identical when you shift it by t naught. Okay, the smallest value of t naught is called the period. So you take sinusoid, you shift it by one period, it looks the same, right? So if a signal and its shifted versions look identical, then it is periodic. That's our simple definition of periodicity. Last question: if a signal x of t with frequency 5 kilohertz is convolved with cosine 5000 pi t, what is the sampling frequency of this signal? Okay, and first of all, I don't like this convolution of two periodic signals, right? Because remember, convolution is an infinite integral, improper integral, and if the signal lasts forever, that convolution is not defined. So that is not quite right. I don't want you to convolve two periodic signals, right? I mean, I gave this caution on the very first day. We are doing improper integrals, so you have to always ask the question: do they exist? Right? Is the answer not infinity? Only then it is interesting. I have a feeling if two convolving functions are periodic signals, then the answer might be infinity. So not easy to answer offhand, right? So don't do it unless you have to do it, unless you know what the answer is. Okay, okay. So see you. Bye.